Yes. Okay. So today, Dr. Imoto will be talking about the universal quantum computation using quantum annealing with the transverse-field Ising model. So, Imoto-san, please start your talk.
Okay, uh, so can you hear my voice?
Yes, of course. Yes.
Okay, okay, it's great. So thank you for so nice introduction, and so I'm happy to presentation my work in this seminar. And so today, I talk about the universal quantum computation using quantum annealing with transverse magnetic field sizing model. And so yeah, so this talk is based on this archive paper. So please check it. So if you're interested in my talk. Okay, so let's start introduction. Okay, so at first, so I'd like to talk about the main result of my work, and so main result consists of the three parts. So first, so we propose the method to prepare the arbitrary superposition state from the ground state using adiabatic dynamics and degenerated Hamiltonian. And so next, so using the above method, so we propose that another way to realize the universal gate set using only the transverse Ising model. And so specifically, so we perform the universal gate operation using the quantum annealing with only transverse field Ising model. So yeah, so we should remark that so we don't use non-stochastic Hamiltonian. So yeah, so all connected to XX interaction. We don't use it. And so finally, we demonstrate our approach using the derivative so experimentally. Of course, so we demonstrate so our scheme so numerically. Okay. 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 So first, I talk about the gate-based quantum computer, and so yeah, so gate type quantum computer so can so perform the universal computations, and so this type quantum computer so okay, so for procedure of so gate type computations so consists of three steps. And so first, so we prepare the initial state such as so there and so there state. So like this figure. And so next, so the initial operator corresponding to the algorithm is acted on the initial state. So in the figure, so this part. So this is the other market, and so this is the X operation, and so C not gate. Yes. And so finally, so calculation result are derived by measuring the final state. So here, this is the measure. And so we can obtain the so calculation result. Okay. Oh, oh. Okay. So next, we introduce the universal gate set, and so arbitrary unitary operator can be realized by combination of the several operators, which is called the universal gate set. And of course, so there are several variations of universal gate set. But so today, so we consider so one of the universal gate sets. So this type we consider, and so so in this case, so this is the X rotation gate, and so this is the Z rotation gate, and so this is the C naught gate, and so this is the 2-qubit gate, and So this is so this universal gate set is so called a continuous type so universal gate set. So theta so we must so choose the so theta so continuously, and so the discrete type universal gate set is known, and so today we consider this type universal gate set. Okay. So next, so we introduce the so quantum annealing, and so quantum annealing is proposed as a method to solve the combinatorial optimization problem. And so first we define the annealing Hamiltonian as so this one, and so HD is the driver Hamiltonian, and HP is the program Hamiltonian, and the capital T is the annealing Hamiltonian. And so probably so many people in this seminar so knows so this slide, but so we should talk about so this so explanation of QA to confirm the notation. And so yes, and QA consists of the three steps. And first, we prepare the ground state of driver Hamiltonian as the initial state. So here, this one. And so next, we let the initial state involved by the annealing Hamiltonian. So this one. And from so small t equals 0 to small t equals capital T, so adiabatically. And so finally, so we estimate the final state by above process and obtain the result of computation. Yeah, so if we to prepare the ground state of so program Hamiltonians so by this so procedure, so we can obtain the so we can solve the combinatorial optimization problem. Okay. And so, yeah, of course, quantum annealing has a good point and bad point. And so we should remark several points. And so first, so QA device with 5,000 qubit device is developed by the US INQA. And so it is relatively easy to scale compared to the gate-based quantum computer. So yeah, experimentally. So it can only execute specific algorithms, and so quantum acceleration is not guaranteed. Yes. Okay. So next, so we talk about how to create arbitrary superposition state by our approach. Okay. So first, so we okay. So this figure shows the energy spectrum in conventional quantum annealing, and so this is energy, and so this is ground state, and so transverse I think transverse field, and so here this is ground state of I think model, and so if we perform the dynamics adiabatically, so we can obtain the ground state. So here. So if we consider the degenerated Ising model as a program Hamiltonian, so this one. So the ground state of the Ising model has so two ground states. And so if we perform the so QA, so adiabatically, so we obtain the so superpositioned state. And so in our approach, the amplitude of the superposition state can be controlled by adjusting the longitudinal magnetic field during the process. And so, so I explained this means longitudinal magnetic field during the process. So next page in detail. Okay. So let's consider the okay. So first, annealing Hamiltonian is given by this one. So we consider, and so we should remark okay. And so HD is the driver Hamiltonian, and so HP is the program Hamiltonian, and so HC this one is longitudinal magnetic field, and so we should remark that so if so small t equals 0, so annealing Hamiltonian is only HD drive Hamiltonian, and so small t equal capital T, so annealing Hamiltonian is only program Hamiltonian. Okay, and so if the ground state, if the ground state of the program Hamiltonian is degenerated, so the final state by adiabatic quantum annealing is given by this state. And so phi 0 and phi 1 are degenerated ground states of the program Hamiltonian. And so alpha is the amplitude of phi 0. Okay. And so the amplitude alpha is also controllable by adjusting the longitudinal magnetic field HD. So here, so we can derive the analytically the relation between the strength of longitudinal magnetic field HD and the amplitude alpha. And so this relation is written in this paper, but today we don't talk about it. Okay. Okay, so let's show the example. So GHZ state case, and so if we consider this Hamiltonian as a program Hamiltonian, so this equation 6, and so this Hamiltonian, okay, so the sigma IZ means the Pauli matrix, and so this Hamiltonian has degenerated ground state, or up state and or down state. So thus the ground state of this Hamiltonian is given by this one. And so we remark that if 1 over square alpha equal 1 over square 2, so this state is JTD state. And so we can control our alpha the strength of longitudinal magnetic field during the QA. Okay, so next so far we discuss the creating arbitrary superposition state. So next so we consider the how to realize the gate operation by our approach. Okay, so first, we consider the X rotation gate. So which is including the universal gate set. This one, this X rotation gate. And so to implement the X rotation gate operation, we consider the following X rotation gate Hamiltonian as the program Hamiltonian. So this one. And yeah, of course, so this is identity operator. And so this Hamiltonian has two ground state. Of course, so arbitrary state have the same energy, but so we consider the so up state and down state as the basis. And so thus, so the final state is given by so alpha up state plus so this so yeah 1 minus alpha square n square root down state. And so the amplitude alpha is controllable by adjusting the longitudinal magnetic field, so Hz. So in this case, the rotating angle is controllable by the Hz. So amplitude of upstate and the downstate. Yeah, so yes. And so next, we consider the C naught gate. And so in this case, so we consider the so this Hamiltonian as a program Hamiltonian, and so we call the C naught gate Hamiltonian. And so sorry, so this is so this sigma 1 hat means so sigma 1 hat z. So yeah, the component of the power matrices. And so A, for this A is more than 0 and less than 1. Yes, one real number. And so this Hamiltonian has so this energy spectrum. And so from this figure, so we observe that so first qubit, so this one is up state. So this Hamiltonian, so this state is not degenerated, but so first qubit, so this one is so downstate. So this so qubit are degenerated, and so in this relation, from this relation, so by using this Hamiltonian, so we can implement the C-naught gate. So yeah, so if so only if the first qubit is a downstate, so second qubit is so acted on the up by rotating operation. Okay. Okay, so this is overview of our gate operation. So first, so if we so prepare the so superposition state and the amplitude, so excited state, amplitude of excited state is alpha, and the amplitude of ground state is beta. And so first step, so we control the amplitude of degenerated ground state. So by our approach using the longitudinal magnetic field, so here, and so we can obtain the superposition of identical energies, and so we can and the amplitude of so these so states are controllable by using so the strength of longitudinal magnetic field. And so next, so we add the longitudinal magnetic field to so resolve the degeneracy. So here, so we can obtain here. And so finally, so we perform the adiabatic time evolution from the Ising model plus longitudinal magnetic field from here, this one, to the transverse magnetic field, so here. And so this step is corresponding to the Admar gate. And so we obtain the first excited amplitude of first excited state is alpha dash, and the ground state of amplitude of ground state is beta dash. Okay, and so finally, so we should so note the rotation gate. So since that rotation gate so it is difficult so since the rotation gate cannot be realized using degeneracy, so it is realized by the relative phase created by the energy difference between the excited state and the ground state. And so um, this method is so they used in so many superconductive qubit um, to implement gate operation. And yeah, and so from the relative phase, and so yeah, and so if we are the X rotation yeah, so we performed the X rotation gate by this scheme. So X rotation gate is realized by inserting the longitudinal magnetic field, and in this case, so yeah, so we can realize this state, and so from the relative phase, so that rotation gate is realized by adjust time, so small t. Okay. Okay, so this is the construction of the gate time quantum computer by our scheme, and basically, we consider the transverse field here, as ring state, and so if we need to gate to perform the gate operation, so 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 we so try we perform the QA operation. So according to corresponding to desired gate operation, and yeah, so gate-based quantum computation is performed by sequentially repeating the gate operation. Okay. And so this is numerical simulation of our scheme, and so this figure shows the X rotation gate, and so the amplitude of X rotation gate can be controllable by adjusting the strength of longitudinal magnetic field during the work process. And yeah, so HZ means strength of longitudinal magnetic field. And so these two figures mean C naught gate. And so the first qubit, so this is the initial state, and so initial state, so first qubit of the initial state is the process state, so this one. So X rotation gate is applied to the second qubit. So this is second qubit. Yeah. However, the first qubit is initial. So first qubit of the initial state is the minus state. So this case. So if we change the HZ, so the state is unchanged. Okay, so therefore, so this our scheme is so yeah our scheme performed the C naught gate, and so finally so we show the experimental demonstration by the device, and so this is the X rotation gate, and so this is C naught gate, and so from these figures, we can observe so our scheme realize the rotation gate and the C naught gate. And yeah, of course, I want to try to perform the so she not gate with so initial state so with another so the other initial state but dual device can prepare only so the ground state of the so transverse magnetic field so we can so prepare only so or plus state. Okay. Okay, so let's summarize our talk. Yeah, okay, so first we propose a method for creating superposition state using degeneracy adiabatically. And so next we propose the X rotation and C naught gate using the above method. And so we propose some method for constructing so gate-based quantum computing with a dual device. And of course, so we can so implement so we can construct okay so dual device and so finally we demonstrated the part of our scheme using the dual device so experimentally and so this talk is based on so this archive paper so please so check it if you interested in my talk. Okay, so thank you very much.
Okay, Imoto-san, thank you so much. Very interesting talk. So any question or comment from audience? So please switch on your microphone if you have a question. So, okay, I have a couple of questions actually. So, okay, my first question is that related to the universal gate set for your setup. Actually, can you show your page 6?
6 just a moment.
Yes, page 6, please. Yes.
This one?
So yes, right. And you realize that the X rotation and Z rotation, and this means that it's quite powerful way to realize this kind of the universal gate set. And but people working in the quantum computation, we usually use not this kind of the operation, but using the T gate and the H gate and also the C naught, right? And in this sense, I guess that you can also realize the T gate, right? Using the Z rotation.
Yeah, of course. So yeah, so T gate and yeah, so the so basic so discrete type universal gate set consists of so T gate and so preferred gate. And
yes, right.
yeah, and so there so this type gate set is constructed by so these three gate set. Okay, so therefore, yeah.
No, you mean that no difference,
yeah,
right?
yeah, not different,
Essentially.
and so yeah, yeah.
Okay, I'd like to know the advantage for realizing not the THC not, but this kind of the X rotation, Z rotation, C not. So
Yeah.
if you have a kind of the advantage, it's quite wonderful. But you mean that there are no essential difference. Okay, thank you.
Okay,
So any
thank you
question?
very much.
Yes, thank you very much. Yes, good. So any question, comment from audience? So we still have a
hi.
couple of minutes.
I have
yes,
a question.
Anna, yes, please. Yes.
Thank you for the nice talk. So I was wondering whether you tried to run longer circuits and see how the fidelity decays and stuff like this.
So okay, so fidelity. So if we okay, so if we don't consider the okay, so okay, so from so when we use so this approach. So we should not we should consider the two source of noise decoherence. So first, so noise from the environmental, and so what? So next one is non-adiabatic transition. So via this operation, and of course, so we can not avoid the coherence from the environment, but this but the coherence from non-adiabatic transition can be suppressed by capital just a moment. So capital T is sufficient. So we choose the capital T. This one sufficiently long, or so we use shortcut to adiabatic technique. And so when we use the shortcut to adiabatic technique, so maybe we probably we our approach can be suppress the coherence from environmental energy, because the time to operating to get operation is effectively short. Okay, so is it okay?
Yes, thank you.
Okay, thank you.
Okay, Anas, thank you for your question. So any question? Comment?
I have a quick comment. So
Yes,
you
please.
plotted
Yes, please.
the populations, but you didn't really plot the phase. And I think the phase will be different, depends on the state you start with. So even though it looks like a CNOT gate or an X gate from the point of view of your population, there's also an overall phase that is different depending on the state you start with.
Okay, so yeah, so of course, okay, so thank you, nice comment. So the relative phase is very important for program. So in our approach, but so we can suppress the relative phase using the longitudinal magnetic field. So in this part, and so of course, so this is I think model, and so two state have same energy. So but when I add the longitudinal magnetic field to I think model, so ground state has different energy, and so if we choose the optimal longitudinal magnetic field, so we can suppress the relative phase. So that is okay.
Well, you just need to keep track of it, right? It sounds like it's something to suppress. You need to know what exactly is the phase that has accumulated.
Sorry?
So the phase is a number, right? So you either need to show that it is exactly zero, or you need to keep track of what it is so that in your computation you can offset it.
So So your question is so how to obtain the optimal longitudinal magnetic field.
No. He asking about so did you check the phase of your quantum gate operation in your numerical simulation? Okay, you can, of course, definitely get the information of phase, but in your slides, there are no information of phase. So then he worrying about that phase. Yes. Yes.
This one. Okay, so in this in this talk, we don't check the relative phase so numerically.
So I think it is
you can do that. Yes.
It's just a comment.
I agree. Yes, I agree. Yes.
Okay. I understand. Okay, I try. Okay, thank you very much.
Good. So any question? So we already over the yes.
I've got a quick question, if you don't mind.
It's okay, of course. Bobby, please. Yes.
Thank you. So I'm perhaps a tad confused. If we just stay on this slide for a moment, it feels like your computational states that you're measuring here are, let's say, plus and minus. Oh, like your energy states, right?
Yeah.
Which are plus and minus. So here,
okay,
population from plus to minus, vice versa. This is perhaps more of a conventional Z gate. Well, okay, so you started with some plus.
Yeah, so plus.
And you end up in minus. So I wouldn't call this an X gate, right? Because an X gate acting on plus should just introduce a phase and no population transfer. So to me, this is a conventional Z gate, not an X gate as such.
Okay, so this this is when we consider this overview. So here, we consider only plus state. Of course, the transverse magnetic field has two ground states. So plus state and minus state, and so we consider the only plus state, so beta equal 1 and alpha equal 0.
Yeah.
And so next here, I think model has up state and down state, the ground state. And so here we we can obtain the first proposition of state, the ground state of the new model. And so here, we obtain the up state and down superposition. So using the up state and down state. And so finally, here, this is transverse field, and we obtain the plus state and minus state. So this is plus state and this is minus state. Yeah, and final
perhaps
steps correspond to the at the margin.
Okay, but let's say from your plot, right, you go from plus to minus, right?
Yeah.
That I wouldn't describe that as being an X gate, right? Unless I'm missing something.
Okay.
But if it was just a black box and you put in plus and I got out minus, this doesn't seem like an X gate to me.
Okay, so in the in numerical, this numerical simulation showed that here, this part, and so if we prepare the first state, So in this part, so we obtain the superposition of the superposition state with so this amplitude, so population or amplitude. This is so the population is equal to the amplitude. So therefore, so we can so perform the exploitation gate. But of course, so we should so show the just a moment. So we should show the so the result of so comprehensive so gate operation so scheme so numerically. And so if you are interested in my talk, so this so the numerical simulation result is written in this paper. So please check it.
All right, thank you.
So okay, thank you very much.
Okay, thank you so much. So time is up. So let's thanks to Dr. Imoto again. So okay, thank you so much. So okay, so Paul, do you have any announcement from the INQA? No.
No.
Okay.
Shiro, thank you, Dr. Imoto. Very interesting presentation.
Okay. So okay, I'd like to close today's INQA seminar. Thank you very much. Bye.
Thank you very much.